Face models derived from 3D databases primarily focus on adult faces, often employing linear or nonlinear morphable models to delineate facial shape and appearance variations. Recent advances in developing infant face models represent significant progress, though they originate from small, curated datasets with limited variability, restricting their scalability and generalizability. Hence, we present INFACE, the first 3D infant face model made public, trained on a large-scale dataset of incomplete face scans using an autoencoder. Many scans in our dataset exhibit artifacts due to camera limits and typical infant scanning challenges, such as varying head poses, occlusions, and movements. We developed the visualized custom blender tool to manually segment those artifacts that may affect registration and model training. We implemented an advanced landmarking approach, deploying 112 points to navigate around these corrupted areas, as they sometimes obscure typical landmarks. Beyond pinpointing standard markers like eye corners and glabella, our scheme also traces curvilinear facial features, such as eyebrows and nasolabial folds, through series of interconnected landmarks, allowing the template to align accurately by iteratively matching these curves. We manually segmented on average 16% of the facial geometry in our dataset as artifacts. The spatial distribution is visualized on the left. We additionally marked on average 27% of the textures as corrupted, as visualized on the right. We visualize our custom surface registration based on non-rigid iterative closest point. Our comprehensive landmarking scheme ensures precise correspondence in unoccluded regions, while excluding affected areas from the registration. Our curated dataset comprises 2,400 registered scans from over 800 different infants. The infants were scanned over multiple month intervals exhibiting uncontrolled expressions. We trained 2 separate autoencoders. One on geometry and one on texture. Each model was trained to reconstruct only the unmasked regions, thus yielding powerful completion capabilities. We adopt an unsupervised neural network training approach for expression disentanglement to accommodate for the uncontrolled expression space in our dataset. We further extend the approach to also disentangle the age from identity and expression, leveraging scans of the same patients acquired at multiple month intervals. We now detail the training setting to learn this disentanglement. During training, 3 scans from the same identity are sampled. The first 2 were taken on the same day, whereas the last was taken on a different day. The model now encodes the age of the first scan. Afterwards, an expression invariant transformation is applied to the second scan before encoding its expression. Lastly, the model encodes the identity of the third scan, which has a different age than the first 2. These 3 latents are concatenated and fed through the model decoder, thus yielding a reconstruction with the expression of the second scan, and by choice design of the 3 scans, the encoded age and identity should also match that of the second scan. Hence, the cross-consistency loss is computed between the reconstruction and the original second scan. For the second train loss, a scan of another identity is added to the triplet. The model now encodes the identity of the added scan, the expression of the first scan, and also the age of the added scan. The shape, decoded from these 3 latents, should now look as if the added scan was making the facial expression of the first scan. As proposed by the original authors, leakage of identity features into the expression code is discouraged by performing as rigid as possible deformation from the added scan to this reconstructed scan using randomly sampled vertices as anchor. The model then encodes the expression from this deformed reconstructed scan again, and concatenates it with the encode identity from the third, and the encoded age from the second scan. The mesh decoded from this final latent should then resemble the first scan, with the identity and age being transferred directly from the third and second mesh, whereas the expression is transferred from the first mesh through an extended pipeline. The resulting self-consistency loss is added to the cross-consistency loss described previously, yielding our final loss employed for this unsupervised disentanglement training. The following plots demonstrate that the model's identity encoding on the left correlates with the actual identities marked in distinct colors, whereas the expression encoding is more uniformly distributed, indicating at a successful disentanglement of the identity from the expression. We now visualize a continuous interpolation through the expression space on a sampled identity with average age. The age can also be continuously decreased and increased. We now visualize 4 additional sampled identities, doing the same facial expressions at a young age at the top and an older age at the bottom. To improve texture realism in the model reconstructions, we follow previous work and train a Pix2-Pix-HD network for high detail infusion into low-resolution vertex colors, tailoring the method towards a constrained texture and painting task. During training, randomized regions of high-frequency textures are replaced with our model's low-frequency reconstructions, achieving realistic shape and appearance completion at test time. We showcase that this realistic 3D in painting can be used to mend occlusion-related gaps and to correct cleft lip deformities in 3D scans. These results underline the model's utility in simplifying scan capture and enhancing infant care by providing a valuable tool for surgical planning and improved communication through realistic visuals. We use INFACE for the challenging and ill-posed task of 3D reconstruction from single images. Given a set of landmarks predicted on the 2D image of a baby, we follow previous work and optimize camera and latent model parameters to align with the projected landmarks, while enforcing regularization to control deviation from the average latent model vector. Here, we showcase selected images from a publicly available dataset and compare the reconstruction results of INFACE with the popular adult-oriented face model Flame. The results demonstrate the superior performance of our method in accurately reconstructing infant faces when compared to Flame, which fails to capture distinct facial features of infants. Lastly, we demonstrate that INFACE can be used to neutralize facial expressions of infants. The scan on the left is reconstructed, and then neutralized in the center. On the right, another scan of the same identity with a more neutral expression is shown as comparison. This application shows potential to enhance data quality and enable standardized assessment of facial morphology. Thank you for watching.